Hmm. We shall today see the aspects of the petroleum reservoir. So previously we had seen the characteristics of source rock and how the petroleum gets generated. Now from the source rock where the hydrocarbons are formed, they migrate to the reservoir rock. So the petroleum reservoir is a very important feature of the petroleum system in which the hydrocarbons they suffer the primary migration. So as I have already told you that the primary migration is from source rock to the reservoir rock. And secondly, within the reservoir itself, there is the secondary migration. So the reservoir rocks, they are the rocks which hold the oil as well as they are also responsible for the secondary migration, which makes them to be known as the carrier beds. So let us have a look at the details of petroleum reservoir. So uh, these are the beds which store the hydrocarbon after migration from the source rock to the reservoir rock, also known as carrier beds. And most importantly, for the rock to act as a reservoir rock, it must have porosity as well as permeability. So if you see in this diagram over here, the porous rock, which is this, it holds the oil. So now as we previously saw that let us say that this is the source rock, and after the oil gets generated it must have an overlying or an adjacent porous rock in which the oil or the hydrocarbons will migrate. So as they will enter over here, this rock becomes the reservoir rock. So why this oil or hydrocarbon move in this rock? Because it has porosity and it has permeability. So we shall see the different aspects of the reservoir rock. Now reservoir rock has to have porosity. And how do we define porosity? These are voids. Voids means the space, empty space. These are voids within a rock created due to grain contact, and it constitutes the porosity or pore space. So if you see in this diagram over here, in the first diagram, you can see the grain to grain contact between within the fabric of this rock, and in the second you can see the shape of the grains is different and their pore spaces are also different than the previous one. So if the porosity of sedimentary rock, it is defined by what are the type of grains, grain size, and what how are they in contact with each other. In the third picture you can see that this is a crystalline rock, and therefore it has no pore spaces in it because there is no void over there. Okay, so the pore spaces, they are generally filled with connate water, but it may also contain oil and gas within a field. So it is these pores, actually it is within these pores it will consist gas, oil, or water, and on the basis of that it can be named as an aquifer or a hydrocarbon reservoir. Porosity is measured in percentage and is represented by the Greek letter phi. So porosity percentage can be calculated as the total volume of the voids upon total volume of rock into 100. Means we calculate the total amount of the empty spaces divided by the total volume of the rock, and then we multiply it by 100 to get the percent porosity. Now porosity uh, is important for the reservoir rock, because imagine that this is if this is the source rock over here and it is overlain by a crystalline rock. If this rock is a crystalline rock, where there are no pore spaces, then oil will not be able to migrate in this. But if this rock is a porous rock like this, if these are the grains, okay, and the voids, these are the pore spaces. These are the pore spaces. So what will happen? The oil will migrate from the source rock and will get locked in these pore spaces. Okay, so this is the migration of hydrocarbon. Now it stays in over there. Okay, all right. So remember this formula. Now pores, they are generally of three basic types: the catenary pore, cul-de-sac pore, and closed pore. So when we say catenary pore, it is this. It has it has this is the pore, and it has a throat. This portion, this and this, they are called as the throat of the pore. So this is a conduit or a pipe like structure which is open from two sides, and this is called as a catenary pore. The cul-de-sac pore, it is having only one throat, and it is closed from the other end, while the third type of pore is the closed pore. You can see that this pore cannot communicate with another pore. Now these three pores, they constitute the absolute porosity, while the effective porosity is constituted only by the cul-de-sac and catenary pores. So this is the effective porosity. Why effective? Because this is effective in the transmission or the movement of the fluid or liquid through these pores, while the closed pore, which does not have any communication with the other pores, it is called as the ineffective porosity. So there are several factors which will define when how a catenary pore or a cul-de-sac pore may form. So in this left hand side picture, you can see that this is a cul-de-sac pore, where you can see that it is closed from one side, and then only one side is open. Okay, so this is the throat of the pore, while the catenary pore, you can see it is connected to other pores through several throats, while the closed pore, it is a completely locked pore with no communication at all. So the hydrocarbons can emerge from catenary and cul-de-sac pores, while closed pores are unable to yield hydrocarbons. And size and geometry of the pores and diameter and tortuosity of the connecting throat passes affect the productivity of the reservoir. So for example, we have a structure like this, and then there is these are the sediment or mineral grains, and we have this pore over here, it is the catenary pore, and this catenary pore, these are the throats. So if this is a pore, so it is open from this side, this side, this side, and this side. Okay, so this will be called as a highly productive reservoir. Highly productive because here the pores the pores, they are quite open, and they have these throats are well connected to other pores. But imagine that if the same throats, they are very torted like this. So even though this is a catenary pore, but you can see the shape of the throat is not smooth like the first case. So here this may not effectively transmit the fluid. So this may become a less productive reservoir. So that is what it is written over here, that the tortuosity of the connecting throat passages, they affect the productivity of the reservoir because they may not allow the free flow or the effective movement of the fluid. Okay, so we saw that on the basis of their structure and their interconnectivity, the pores are of three types, which were the catenary, cul-de-sac, and closed pores. While on the basis of the time of formation, the types of porosity, they are of two types: the primary or syn depositional, and secondary or post depositional. So syn depositional porosity, it is formed as the at the time of sediment deposition, while the secondary or post depositional is the porosity that forms after the sediment deposition. Now there are several ways in which it may form. So you can see over here that for the primary or depositional porosity, one way is sedimentation. So what happens over here is that here you will be finding intergranular pores. So this is one grain, this is another grain, this is the third grain, and you can see that within these grains a there is the development of the pore. So this is the pore here, then this is the pore. So these are all intergranular pores, while once the porosity is within the grain itself, you can see over here, these are the pores within the grain. So these are intragranular pores. This is the pore, then this is the pore. They are developed within the particle or the grain. So these are called as intragranular pores. Then we get the fenestral pores. Fenestral pores, they are normally formed by cementation when there is the excess growth of the cement over in the rock. Then what do? They fill up the space at some places and then they leave voids at other places. They are called as fenestral pores, while intercrystalline pores within the crystals between two crystal grains, once the pores develop, they are called as fenestral pores. Their origin is because of the cementation. Then the wuggy or moldic pores, sometimes there are several rocks which are very prone to dissolution. So once the dissolution happens, it selectively removes the fabric from the so it removes the grains from the fabric of the rock, leaving behind a void that makes the wuggy or moldic pore. While due to tectonics or compaction or dehydration or diagenesis, fractures may develop. They are again the secondary porosity. So these fractures, if let us say for example, this is the basement rock, and over it lot of pressure is being put by the overburden, then these rocks tend to fracture. They may develop fracture in them, and these fractures, they are planes of weaknesses. They may lead to the development of porosity, but these are formed after the rocks or the sediments have been deposited. So they are all secondary or post depositional porosity. So the brittle rocks, they tend to fracture in three geological settings. That is the crest of the uh, anticlines, where the uh, at the crest, due to the high tension, the fractures may develop. This is one location of the development of fracture pores. And then the lowest point of a syncline, that is where compression happens, there again the fractures may develop. So these are one of the locations where they may develop. Then adjacent to the faults, over here in this adjacent to the faults, these fractures may develop, and then these fractures may also develop beneath the unconformities. So what happens over here is that these three types of settings, they are important for the development of fracture porosity. Fracture porosity is a type of secondary porosity that increases the storage capacity of reservoir. How? So this fracture porosity, it increases the reservoir capacity. How? Because they increase the permeability. Increase the permeability. So they are very commonly found in brittle rocks like sandstone, limestone, shales, igneous rocks, metamorphic rocks. So we can find them in sandstones, we can find them in limestones, then they may occur in shales, occur in igneous and metamorphic rocks. You will come across several words like the uh, fractured basement reservoir. Sometimes the oil or hydrocarbon may be found in igneous rocks. We all are aware that igneous rocks don't have the capacity to generate hydrocarbon, but they may act sometimes as reservoirs only by the development of fracture porosity. Okay, so this was about the porosity. Now let us look at the second important feature. See, porosity is not enough unless and until the pores they have the ability to communicate with each other, means that they are connected. So capacity of a porous material to allow fluids to pass through it by interconnectivity of pores, it is called as permeability. So in this diagram you can see that all these are pores and they are interconnected so that they may allow the flow of hydrocarbons. In the lower diagram, if you see here, the crystalline structure, it makes the fabric non-porous and non-permeable. While in the second one, you can see these are porous, but they are non-permeable. Very common examples are shales. Here you can take any crystalline igneous rock, while the porous and permeable rocks, for example, sandstones. So here you can see that the pores are interconnected to each other and they may facilitate the flow of fluids. While in shales, even though they are porous, but they are non-permeable because the pores are not interconnected. So this may happen on based on several factors like the number, geometry and size of interconnected pores, capillaries and fractures. So permeability is normally an intrinsic property of porous material and it governs the ease with which the fluids move through hydrocarbon reservoirs, aquifers, gravel packs and filters, etc. So what is permeability? It is defined in units of area which relates to the area of open pore space in cross section that faces or is perpendicular to the direction of the flowing fluid. So if you uh, uh, get a bit confused about this definition, simply remember that this is the interconnectivity of the pores and it is measured in, it is kind of an area. It is measured in the units of area. And the SI unit for permeability is meter square, but the more popular and common unit of use is Darcy. Darcy. So 1 Darcy is equal to 10 to power minus 12 meter square. It has been found out that most reservoirs have much lower permeability, less than 1 Darcy. So, milli-Darcy term is commonly used. So, 1 Darcy is defined as the permeability that allows a fluid of 1 centipoise viscosity to flow at a velocity of 1 centimeter per second for a pressure drop of 1 atmosphere per centimeter. This is how 1 Darcy is defined. So Darcy gave this law for the dynamics of the fluids, and then he gave a formula. So you should remember this formula: Q is equal to K P1 minus P2 upon mu L, where Q is the rate of the flow, L is permeability, that is delta P is the pressure drop, A is the, sorry, here it will be multiplied by the area. Sorry, A is the cross sectional area of the sample. L is the, and this is K. I'm so sorry, this is K. K is permeability, L is the length of the sample, and mu is the viscosity. So by applying this formula, you can calculate how much fluid is going to pass through a certain opening or a porous and permeable rock. Remember that the Darcy law is only valid when there is no chemical reaction between the fluid. Say for example, you have a carbonate rock, and this carbonate rock has developed secondary porosity, and it is filled with an acidic fluid, or a fluid which has got a lower pH. So let us say that this is a fluid of low pH, means acidic. So what this will do, it will keep on dissolving this carbonate, and this will lead to the formation of wugs or moldic porosity. The pores will get bigger and bigger, and then the whole this uh, relationship goes wrong over here. So what will happen? So what will happen over here is that the Darcy law holds valid only for the situation where the pore shape and size, they remain intact, they are not going to change. And then second thing is that only one fluid phase completely fills the pores. So imagine if you have water and oil both in the rock, then the water being denser than the oil will behave differently. So there, this Darcy law becomes invalid. Okay, now that we have seen what is porosity and what is permeability, so let us see the relationship between the porosity, permeability, and the texture. Because texture of the rocks, it has a direct correlation with porosity and permeability. The texture of a rock is related to the original depositional fabric, and the fabric may also be changed by the subsequent diagenesis. So we can see here that porosity and permeability permeability, they are dependent to a large extent on the texture of the rock, but at the same time they may be modified by diagenesis. Now, diagenesis, it starts as soon as the sediments are deposited. So what happens is that sediments may see the growth of new minerals. Sediments may witness the solution or dissolution. Sediments may come across extreme solution or karst processes. So this diagenesis has a great impact on the porosity and permeability of the reservoirs, and we shall discuss that in the next class. But today let us see what are the textural parameters of loose sediments that may affect the porosity and permeability. First one is the grain shape, where roundness and sphericity. So remember, roundness, it is the degree of angularity of the grain. So we will call this type of a grain as angular grain, while we may call this type of a grain as a round grain. Then sphericity, it is the degree to which uh, a grain goes closer to the spherical shape. So you may have an angular grain which is spherical. This is a spherical but angular grain. So this is spherical, angular. While you may have a non-spherical and a round grain. Non-spherical and round grain. Okay. Second is the grain size. You all are aware about the Adin-Wentworth scale. then sorting, poorly sorted, moderately sorted, or well sorted, and then fabric packing, that is the grain packing and grain orientation. These are the four most important textural parameters that affect the porosity and permeability of the reservoir rocks. Okay. So if we come to the first aspect, that is the grain shape, it is having sphericity, as I just explained, degree to which a particle approaches spherical shape, and roundness. So porosity might decrease with sphericity because the spherical grains may be more tightly packed than subspherical ones. So what does this mean? If we have a perfectly spherical grains, they may show very tight packing. They may show very tight packing. So once the tight packing is there, it may lead to a decrease in porosity. But if the grains are rather less spherical or subspherical, then you may witness higher porosity in them, like that. Okay, so this is a very qualitative. And you can see here how the increasing roundness and high and low sphericity have been explained in this diagram. So you should remember that porosity might decrease with sphericity. So the more the spherical the grains are, the lesser the porosity might be. Second is the sand size. So we all are aware about the different types of uh, grain sizes. Sorry, not sand size, grain size. So we have the classification of the sediments as gravel, then we have sands, and then we have clays. So the gravels are too big to be considered to be the rock forming material. They may of course be quite larger in size. The coarser sands, they are one of the best type of reservoir rocks, and where they have higher porosity than finer sand. So we all are aware that if the grains are bigger like this, grains are bigger, they tend to have higher porosity. You can see over here in this diagram, I don't need to draw it again. Over here you can see that the coarser sands, they have higher porosity, but the finer sands or the silt, they have lower porosity because they tend to get mixed in the intergranular spaces and they reduce the porosity, while the permeability declines with the decreasing grain size because pore diameter decreases and capillary pressure increases. So what happens over here, if you have the very small grain sizes like this, there the interconnectivity between the pores might be very less. That is why the as the pore diameter decreases, definitely the interconnectivity between the pores shall decrease and permeability will be reduced. So uh, the coarser grains, they cause higher porosity, which in turn may give rise to higher permeability, but the finer grains, they have lower porosity and lower permeability. Next is the grain sorting. We all are aware that once the sediments are immature, they are poorly sorted. So when I say poorly sorted, they have the a mixture of the sediments of different sizes. So you may have gravel with the finer clay or finer silt, which are uh, which get placed as the matrix material in which those larger or coarser grains are floating. With time, as the uh, transport of the sediment and the way they are being uh, you know weathered and eroded, it goes on with time, then the finer ones, they are removed, leading to the deposition, or the coarser ones, which becomes fairly or more well sorted. So the degree of sorting is also a degree of the maturity of the sediments, means how much time that sediment has passed in the process of deposition and movement. So porosity increases with better sorting. So for example, if we have sediments like of almost similar size, and this is the example of a well sorted sediment. So with the well sorted sediment, you can expect to get higher porosity. But if the sediments are this way, then we can say that okay, these are the poorly sorted grains, and these poorly sorted grains will definitely reduce the porosity as well as the permeability. So porosity and permeability, they are much dependent on the sorting of the grains. So in this plot over here, you can see how the sorting as well as the grain size, they impact the porosity and the permeability. So if these are the well sorted coarse grains, then you have a higher permeability and higher porosity. If you have very poorly sorted fine grains, then again you are going to get lower porosity and lower permeability. So with this plot, it becomes very clear that how the impact of sorting is there on the porosity and permeability. Next is the grain packing. So as we have been discussing that the uh, well you know well rounded and spherical grains, they may cause very tight packing, which may reduce the uh, porosity. But then once we are talking about the packing, then there are different types of packings. There are almost six different types of ranges, and if you go to my sedimentary lectures, I had told you about the grain to grain packing. But here, in specifically in the sands, these geometries, they may range from cubic packing to rhombohedral packing. Here in cubic packing, you get the uh, the porosity high, almost 48% porosity. So the sands which show cubic packing, they become very good reservoirs, while the rhombohedral packing, it has lower porosity. You can yourself see over here how the packing goes on. It has sufficiently almost half of the packing of porosity of the cubic packing. So porosity increases with better sorting, as we saw previously. But here packing geometries, if this is the cubic packing, we get high porosity. If it is rhombohedral packing, we get low porosity. Okay, these two lines have come from the previous, so you can avoid these. Okay, once we talk about the grain orientation, now remember that it is not only the packing but also how the grains are oriented is very, very important. They both form a very important aspect of the grain fabric. So the grain orientation is more significant to porosity and permeability than packing. The orientation may have little impact on porosity, but it has a major impact on permeability. Because here, how the grains are oriented, if the grains are, quite rounded and spherical, and they are in the cubic packing, we may expect to get uh, higher porosity. But if they are not oriented in appropriate directions, then they are ought to block the interconnectivity of the pores, and porosity reduces. So the if you look at this diagram over here, you can see there is the permeability in three directions, that is kx, ky, and kz. So here vertical permeability is generally lower than the horizontal permeability, because now what is happening over here, you can see, say if the grains are all flaky, like this, and they are stratified, then of course this porosity, or these pores which are over here, will not be connected with the pores over here. So vertical permeability is lower, but these are the pores in the horizontal fashion which are very well interconnected. Now what happens over here, that permeability will be greatest in the direction which is parallel to the grain orientation. So if you see in this block over here, if this is the moving current, then the flakes, they are all parallel to the x direction, so it will be the maximum, followed by the y direction. Like for example, in the cross bedded sands, they may be aligned parallel to the strike of forceps and followed by the vertical. So the permeability in the x axis, along the x axis, is highest, followed by y axis and then the z axis. So the grain orientation is very very important once it comes to the uh, impact on the permeability. So this is all about the porosity and permeability of the reservoir rocks. In the next class, we shall see the effect of diagenesis on the reservoir quality. So from this class, what is the takeaway? First of all, what is a reservoir rock? What are the characteristics of a rock to be classified as reservoir rock? And then what are the different types of textural parameters which are essential for a rock to be classified as a reservoir rock? And therefore, once you go through this lecture, and then you should read the uh, material on the internet or some books, you should try to learn it by heart as well as understand it, so that you can write good answers in your upcoming GSI examination. That's all for today.